Another important question when looking at properties of graphs and properties of formulas, functions, is to ask what happens as we get larger and larger values, or colloquially, what happens as we approach infinity on the horizontal axis. The way we're going to express that, again, in a more intuitive way, is to write the limit as x approaches infinity of a function. We're going to say that equals some number L if we get closer and closer to that value when x gets larger. So let's add a little line here, call that L. And so in essence, we're talking about a horizontal asymptote. If as we move out in the x value, we get closer and closer and closer to that L value, maybe touching it, maybe not, doesn't matter. As long as the further out we go, the closer we get to L, then we have that limit being satisfied. We can also talk about x approaching negative infinity if we're going in the other direction. So say we had this kind of scenario, then this would have a different L value. In fact, here an L value is 0. When we look at functions, especially functions based on formulas that we know, it's important to remember the core graphs of these functions and have those at your fingertips. For example, if we look at the graph of y equals e to the x, there's that graph there. We know that the graph is always positive. There is no point where y equals 0 on this. However, we would say that as we go out to the tail of the exponential, as x approaches negative infinity, in the limit, we would get a value of 0 because we get closer and closer and closer to 0, and we can get as close to 0 as we like. So in the limit as x approaches negative infinity of e to the x, that is 0. With that basic idea in mind, take a moment to think about this limit here and see if you can evaluate what it might turn out to be. We'll come back and do it in a moment. All right. This kind of limit can be worked out in a number of ways. The most straightforward way is to look at where the variable is. Here the variable is t, and it's inside the exponential. So we can ask, what is the limit just of that exponential? Well, this is a negative exponential, so it's an exponential decay. And if we're talking about exponential decay, and we ask what happens when time gets bigger and bigger and bigger, this is going to equal 0. What that means is, when we take the limit as t approaches infinity of this larger expression, 15 minus 10 e to the minus 0.04t, we can focus in on this part here, and often we'll write this as this is going towards 0, and then we can use standard algebra. If this is approaching 0, then we're going to have 15 minus 10, but the 10 is multiplied by 0, and we're going to end up simply with 15. What does this graph look like? It is going to have a horizontal asymptote at 15. We've actually seen this earlier in the course. It's going to be a graph that looks like this. So an interesting graph, and the limit gives us some properties of the graph without actually getting the sketch first. We got this purely from the formula of the function. Let's now look at a rational function where we have polynomials over polynomials. These are a classic example of interesting limits, especially when we go out to infinity, and we'll explore what this looks like. Now, we can't sub in infinity, so I hate to say this. I'll just put it in quotation marks. But the idea is if we put larger and larger x values in both of these places, we would essentially approach infinity over infinity. And this is another one of the indeterminate forms. An indeterminate form means go back and do some more work. Before you try to evaluate the limit, you've got to make this look different. Otherwise, you're going to end up with this expression here. And the nice thing about rational functions is there's a process you can follow with these. In this particular example, we can use a very common trick, which is to take what we have already. We can't change the expression we were given, but what we can do is add and subtract the same amount, or we can multiply and divide by the same amount. And what we see here, or with some practice you experience, is the problem is the fact that we have x squareds that lead to these larger and larger values. If we could get rid of the x squareds, then life would be a bit better. And so what we do is we multiply by 1 over x squared in the top, multiplied by 1 over x squared on the bottom as well, that whole package is the same thing as multiplying by 1. So that's totally safe, it's totally legitimate. What it lets us do, though, is simplify the expression into a slightly different form. We have to distribute that 1 over x squared into the inside there. That's going to give us a 1 plus 1 over x squared. The denominator is going to be a 2 minus 1 over x squared. And now, when we sub in, again in quotes, it's an infinity, but we can evaluate each of these separately. 1 over larger and larger numbers, that expression by itself heads towards 0. Likewise, the 1 over x squared here, if we're plugging in larger and larger x values, x is 1,000, x is 1,000,000, 1 over those values squared is going to be smaller and smaller, and that leaves us with simply 1 over 2. So the limit of this function here, this rational function, isn't infinity over infinity. That's not a definitive answer. We recast it with this addition of the leading terms 1 over x squared over 1 over x squared, so we don't change the value, but it lets us work with a different form of the equation, a different form of the function, and we end up with a nice simple value of 1/2. The general technique here is divide the top and bottom when you have a rational expression like this. And there's two different camps. One is by the highest power of x. Here we had x squareds in both the numerator and denominator, so we just picked x squared. There's a slightly more sophisticated way to do this. Made no difference in this case. But the highest power of x, turns out the denominator is the most important one. Denominator. This one often gives you a little easier algebra when you're done, but if you've learned the highest power of x, that is fine too. Both of these get you to the same place. This just gives you nicer intermediate forms. We'll have some practice problems available for you to experiment with this, and hopefully it's a review for most students, but if it's not, this is the basic guideline for how to approach these kinds of limit problems. There will be more sophisticated limit tools in our toolkit, but we'll see those a little later in the course.